I'm Liam. I believe I know just about everyone here, except for a couple. Second year master's student just about to graduate, fingers crossed depending on how this goes. And so I've been looking at performance counters and how to schedule them, how to get the best performance we can out of them. And I've done that by developing this tool called Saccade. Oh, come on. There we go. Okay, so we talk a little bit first about the world of performance counters. So we can track any number of hundreds of different events on a CPU core. These could be instructions retired, it could be branch miss predictions, cache misses, cache hits, whatever. The challenge is on each core you have a small number of physical counters that you can actually use to track those events. So ranges from 4 to 8 usually, maybe a couple more that are hard-coded to a particular event. And that means you have to choose between covering a wide range of performance counters or getting really high fidelity readings of a particular performance counter. And this is what that ends up looking like. So these are some performance counter traces. And we'll have this sort of measuring system where you've got a dozen different events that you're tracking and 2 hardware counters. So the high fidelity, low coverage strategy would look something like this. You just pick 2 of them, and you look at just those 2 for the entire duration of your workload. And so you learn a lot about these 2 particular events, but you know nothing about the rest of the system. Another alternative is you could do time division multiplexing. So you start looking at these 2, but then when you get to this point, you go and look at these other 2, and you keep going. And so now we've covered the majority of these counters, but for any given counter, you look, we've only observed it for a very small period of time. So maybe here, we managed to get lucky and we actually caught a state transition. But for counter 0, for event 0, we're going to be assuming that it's at that higher rate for the entire duration of the program. Or there was another one that was interesting. Yeah, this guy, same problem over here, right? So we're completely misunderstanding the different phases of the program because we can't actually make observations about everything all at once. And so the way that this is traditionally solved is by doing round-robin multiplexing, which I've just shown you, and assuming constant rates between different observations. So in that previous example, that was a very short example. You'd be rotating at a much higher frequency relative to the duration of the workload. So you'd be catching these counters at multiple points during the program's execution, but in between those observations, you'd assume a constant rate or a linear curve or something like that. And that's what perf does. So Mathur et al., this was back in 2007, I think, 2009, something around there. They did an analysis and they found that 42% of the intervals that they sampled had error over 10%. So this is pretty significant if you're doing series performance work. And that led to some changes in perf to improve this a bit by using some techniques I'll talk about in a little bit. But the problem still remains. So this work reframes this. So instead of thinking about how we're going to do noise mitigation, because all of that interpolation, it just introduces noise into your readings. So existing approaches primarily handle post hoc noise mitigation strategies using fancy models and all that. We're not going to look at that at all. We're going to reframe this and look at it on 2 angles. We're going to look at how we can schedule what counters we're looking at various points in time, and we're going to do an online estimation of the global state of the system, given the limited visibility. So these are your 2 orthogonal axes that we're going to be looking at here. And this leads us to our core research questions. So does closed loop scheduling outperform an open loop baseline on reconstruction error? And so closed loop means that the scheduler is looking at the state of the system as it's making scheduling decisions. How separable are the scheduler and estimator axes, and where do they interact with each other? How do LLM-driven schedulers perform compared to statistical baselines? So we'll talk about the LLM-driven schedulers in a minute. Can we use natural language query structure to affect an LLM-driven scheduler's ability to reallocate profiling effort towards towards particular counters of interest? And then what's the overhead of this whole thing? How much does this cost to actually run it on the program? And so here's where we sort of ended up. This is not spoiling everything here, but so I built Saccade, which is a framework for evaluating performance counter schedulers and estimators. that is the primary technical contribution of this work. It supports a decomposed architecture that frames estimators, schedulers on an independent mix and match components, a collection of estimators, a collection of schedulers, including some LLM-driven schedulers, a mechanism to reconstruct global counter state given multiple runs of the same workload, and then guidance for the optimal configuration of the system based on to achieve some goals. So let's do a little bit of background here on what.
Quick question. What is a global counter trace?
A global counter trace is that trace that I showed you a little bit ago. So observing all counters for the duration of the program, which is not possible on hardware, so we have to reconstruct it. And it's going to be, yes?
Oh, I was going to ask, would like a simulacra of that just being like running it multiple times and just manually changing it?
That's exactly what we do, but there's some tricks that we use, or that I use to make it work out a little bit better because, and of course it only works for deterministic workloads, so we're only looking at deterministic workloads. The idea is you use the deterministic workloads to learn something about the system so that you can use the online system on the workload. That's the theory. Yeah, so, any other questions? Okay, so we'll look a little bit about, this is the perf stack as it stands in Linux. So at the bottom, we've got the CPU core that's actually doing the computations, which is connected to, via the performance monitoring unit to the hardware counters. There's a reasonably complicated infrastructure in the Linux kernel to manage the PMU and the counters. The important thing to know about this whole system is we are going to be replacing this stuff up here. So we're still going to be interacting with the counters through the perf events subsystem, not using perf, the profiling tool. So all of this stuff, with the exception of the overflows and interrupt-driven profiling stuff that perf supports, we're not using that, but we're going to be carving out sort of this component and then plugging Saccade into the top of it. We're going to use eBPF, which is a really sweet mechanism to modify the kernel safely in order to get high throughput, low latency data movement from the counters to user space. There are lots of different ways you can do that. Get read counters from user space for some oddball reasons. A lot of the standard ones don't really work in this application. So there's a eBPF program that gets attached onto the schedule switch trace point and also a high frequency clock, so we can pull the we can sample the performance counters using this mechanism. And then the schedule switch trace point lets us do some bookkeeping when the thread is migrating between different cores. So here's the design of Saccade. Broadly separated into 4 configurable mix and match components, and I'll walk through them in order. So the source is where your actual samples are coming from. So this, in the live system, this is actually what is controlling the hardware. The source is what handles the mechanics of manipulating the counters and like switching out, observing one event for another event. We can also plug in a virtual sample source. So we can run this entire system on a simulated application or a replayed application. The state estimator, so this sends quantums, which are a package of samples on a periodic basis to the state estimator and computes some aggregates of that collection. The state estimator's job is to take these sort of limited, not global quantums and use those to impute the state of the whole system of all of the events. Hopefully that makes sense. So we get 4, 6, 8 readings, and we got to impute 200. And we've got 3 different versions of that, which I'll go into a little later. The state estimator sends this global state estimate into the scheduler and into the output sync. So this is where your actual trace comes from, and you can have it in any format you want, as long as it's one of these 4. And then the schedule. So the schedule is going to send a signal back into the source on what counters it wants to look at next, and it gets input from the state. So we've got 8 different. It's actually 9. It's actually 10, but 2 of them are just slight variations on these 2. And we'll go into a little more detail, but this is the high-level design of the system. Any questions here? So the killer feature of this is that you can mix and match these any which way you want. You can use a simulation, you can use the real hardware, you can have your output however you want. Very flexible, very powerful. These are the key traits that you gotta know to really understand how this works. So this is the only code I'm gonna show you this entire presentation. The estimator and the scheduler traits. So the estimator receives measurements in this sort of format here. And then it propagates error by calling the time update function. So as an estimate gets older and older, the error bounds get wider and wider. So this is how you propagate the error. And then this is a mechanism by which you can recall the estimates from that estimator. And this is the estimate that you get back. And then the scheduler is pretty the interface is pretty straightforward. You've got a way to initialize it with the world of all events that you're scheduling. So you got to know that up front. And then, of course, the number of slots that you can actually observe at once. So on our machine, if this is 6, on your laptop it might be 4. If you find some cool machine somewhere, it might be 8. And then the next step, which he takes in a quantum, which is a packet of samples, runs it through the estimator, makes a decision, and outputs that decision, which is what events it wants to have active and the duration for that activation. And if you don't provide a duration, there's a default, which is sensible. Okay, continue. So here are the 3 estimators that we've implemented here. The propagate estimator, which is very similar to what you find in perf, which is you just assume that whatever the last thing you saw, that's what it is now. No fuss, no drama, very straightforward. Exponential moving average, which is just basic smoothing. So you have a knob that you can configure, but you're doing a little bit of smoothing over your observations. And then the Kalman filter, which is a little bit more interesting. This is a filter that we borrow from our friends over in the probabilistic robotics field. And what we want out is this guy, x hat k. So that is the state of the system, the mean of our, so we're going to represent the entire system as a probability distribution, a multidimensional probability distribution. P is the covariance, x hat is the mean. And we can either update that knowledge by predicting based on some model of how the probability distribution evolves over time, or we can take a measurement and then incorporate those measurements into the model. So intuitively, if you imagine that this sort of 2-dimensional blob here as our state, as we do a prediction step, that's going to get wider and wider and wider, and as you do a measurement step, it's going to shrink down. These sort of pull against each other periodically to maintain this state output. The key here is that because we're not representing these independently, we have the 2D covariance matrix here, which encodes some of the correlation between the different elements of this vector. Any measurement can actually morph the whole distribution, not necessarily just the thing you observe. So the hope here is that by learning something about the relationships between the counters, either in a offline training step or online as the filter runs, you can get a better estimate of the state. Here are the schedulers that we surveyed. So start out with a couple classics, the random scheduler, just pick whatever. Random with reselection, to be clear. Round robin, which is exactly what you think, the time division multiplexing that we saw earlier. Rate of change is a little bit more interesting. This is actually the scheduler that is in perf now. So you keep track of the last 3 observations of any counter And if it's a straight line, that means that its rates are very stable, and so you don't want to look at that as often. But if the 3 points form a triangle, then the intuition is that that counter's rate is changing a lot, and you want to look at it more often. Maximum uncertainty, that picks the counters which you have the highest variance, the least confidence about. So those are our analytical schedulers, and then we've got a few LLM guided schedulers. So the first is a weighted round robin, which is at startup, you emit weights for every event and then construct a round robin schedule based on those weights. And then static, which is you give the LLM full control over a looping static schedule, let it do whatever it wants. And then dynamic is just like static, but periodically you say to the LLM, this is what I've observed, what schedule should I do now? And these two also have so-called like reasoning variants, where you ask it to think about the problem and describe a line of reasoning and then generate the actual schedule. These are included primarily to explore the space of what is possible here, and we'll talk a little bit about their performance in a bit. This is another cool feature of the system, the sweep and simulate, which I alluded to earlier. So in the absence of custom hardware with hundreds of hardware performance counters, we have to manufacture the ground truth to compare against. So we take a workload, run it dozens of times, and we pick a new set of counters to run each time. Of course, the workload has to be deterministic. And in every run, we include the instructions retired event. And that allows us to normalize the different runs against that, because instructions retired one, it's very constant. Like the number of instructions execute per program is going to be very, very, very close to the same. If it's deterministic for every run of the program, it allows you to scale for things like the underlying clock rate or thermal things or all that. And this was added in, and this reduced the noise of this whole sweep and simulate system by a factor of 15 or 20 by doing this normalization. And then we align and merge the individual traces, so you align all the timestamps that align up. And that's how we got that trace at the very beginning, because obviously we don't have hardware that has 16 counters on it, we have to make those up. And then, as we alluded to earlier, you can actually replay these traces through Saccade just as you would. And it goes through the exact same scheduling system as you would see with real hardware. And so this lets you evaluate estimator scheduler, yes?
No, finish your sentence.
This lets you evaluate scheduler estimator combinations against some ground truth. So even if what we swept isn't perfectly correct, it still represents a ground truth that we can compare against when we try to run a schedule on. Yes?
So I'm still trying to think about the Kalman filter that you mentioned earlier. Are you applying the filter on an individual event count or the whole system?
The whole system.
So that is, I think, where my problem is. My understanding of Kalman filters is that one, they assume a linearly changing world. And if you look at the entire system, that is not going to be the case.
Yes.
And they also assume, the filter will typically try to track a single average. So if you have a multi-modal system, like you have performance bottlenecks, and a big chunk of your bottleneck comes from front-end miscalculation, which is front-end bound, and another big chunk comes, let's say, from very slow memory access because you have misses. So you have a bimodal distribution. The Kalman filter is not going to be able to capture that.
The bimodal
right here?
Kalman filters were developed for radar tracking,
Right.
which is three-dimensional problem,
Right.
in which two of the dimensions can change way, way faster than the others.
Right.
Right. So I think
And that's
it's
exactly where they have,
applicable.
but this is exactly why they have been noted that have problems with these distributions. So you try to track, let's say, a shape, which is one thing.
Well, the state here is 222 dimensional here. So the bimodal distribution you would see is, if you had a perfect oracle, that bimodal distribution would be one single point in a 222 dimensional space.
Exactly.
And so-
He's tracking one airplane, not a dozen airplanes.
So then, what is the one thing you're tracking?
So we encode the current state of the rates of all of the counters is a vector. And that vector is represents a point in high dimensional space. And so we're tracking that one point in 222 dimensional space as a multidimensional Gaussian distribution. And this is, the Gaussian assumption will come back to bite us later. Don't worry, I agree with you there. The linear assumption comes back to bite us later too.
Okay.
But there's no reason that a filter of this structure would be unable to track, at least that I'm aware of. There's no reason that a filter of the structure would be unable to track, sorry for the double negative, this space, because it is high dimensional here. So our covariance here, that is a 222 by 222 matrix. So it encodes the covariance between every pair of counters, of events.
And can it respond quickly to changes in execution phases?
That is up to the configuration of the system. And so we will see.
Kind of a research question. You're expecting, you're proposing a bunch of different
This is
integration filters, right? This is one.
so broadly here. I will say that this represents a survey of some of the options available in this space. I am not making any claims that this is the best way to do it. In fact, I will spoil myself a little bit. A lot of these don't work very well, but I'm describing the system so that we can look at it later and make sense of the results.
Right.
And so I'm going to show you, unless I skip something, I'm going to show you a demo. And with any luck, I can do this easily.
You're a brave man.
I have a backup, don't worry. So this is what our interface looks like. I'm just going to run it with the defaults. There are a million configuration options here. There's a configuration file if you so desire. But so we say Saccade run, and that means actually run this program. I want you to actually run this, and we're going to run NAS, the serial version of conjugate gradient in size K. So fire it up, and you get your output, huzzah, and we found 147 samples from the system. I'm not going to dig into the results here, I'm just showing you the interface. And then for sweep, this is what it looks like down here. We're going to run the same workload, but in a smaller size, just so we can move along. And then we're going to output our ground truth trace to the sweep.perfetto file. And the output is in Perfetto format for the fans of Perfetto. So we're going to run it 45 times, so 222 events. That gives us 222 divided by 5 is about 45-ish. 45 runs, and then it's going to stitch them all together, give us our output. And then if we want to replay that, we'll use the simulant keyword. So we have to reference an event library so that we know what events are available to us in that trace. And then we're going to replay this trace through our scheduler and estimator infrastructure. And there we go. It runs basically instantly. I believe so we've got some non-zero values up here. We won't dig into them too deep, but the important thing to show is if I go trace.perfetto and sweep.perfetto, this is sort of the coda thing, right? So this is much smaller. The trace is much smaller than the sweep, which is what you would expect because this is doing that multiplexing, scheduling, observation thing over the sweep. And then this work, oh yes.
I was just going to ask if so at the beginning you kind of showed kind of your multiplexing process for cameras. So like, are you able to describe that easily from an arbitrary scheduler? And like what decisions were made at what time step?
No. Well, it is it's in there, it's just not easily accessible right now. And that was not a focus of this work, but easy to get out if you wanted to. And now, because this worked, I can skip these. I can skip these canned ones. There we go. Okay, so here's our evaluation. So our testbed was Tucson, which is a Dell server, 16 cores, 32 threads, 32 gigs of memory, moolah, and then 6 hardware performance counters per core. These are the workloads, so we've got them divided up here. The workloads that we use to train the Kalman filter, and this was seeding the process of noise. So when you're learning the relationships between the counters in these workloads to seed the noise with off-diagonal covariance entries for that propagation noise, if you remember. Ran on those, not too important. For actual evaluation, we use these 6 workloads here. So integer sort, triangular solver, some other solvers and some math stuff, and then chess engine and some image processing things. Notice here we got 4 pretty short workloads, 2 reasonably long ones, nothing crazy long, and importantly here, as a limitation for work, nothing long enough that you couldn't just run it 44 times and get your answer, right? And also these are all not necessarily instruction by instruction deterministic, but phase level, they are all deterministic. So we'll start by looking at the overhead of the system, and this is where we start to get some interesting results, and one that's hard to explain. So we notice that actually performing the samples, so in the eBPF code, reading from the counters and shuttling those values back to the user space, doesn't really matter how often you do that. You're good. It doesn't really. There's a bit of noise on it, but about 10%. You're gonna get about 10% overhead on your workload, no matter how often you do the same thing. When you do the scheduling is when things get a little bit more interesting. So this is the exact opposite of the graph that I would expect. And if you're looking at this and you're confused, I agree. So that if we run the scheduler, so if we step through the schedule once every second, so this is a very coarse update. It was a sort of a straw man, if you will. We find that the actual overhead goes up by a lot. And I don't have a good explanation for this. There is, the next slide goes into a little bit more detail on this. But for the purposes of the future evaluations, we end up picking a scheduling quanta of 10 milliseconds and then a sampling period of 10 microseconds. So we don't run into this odd edge effect for the future stuff. Here's where some of that might be coming from. One of the major drawbacks of this system is that there's a significant amount of engineering effort that went into it to support 2 things. First of which being multi-threaded applications, and the second of which being system-wide monitoring. And so in order to support that, there is a world stop that is performed to stop capturing samples while you are changing the count, reconfiguring the PMUs on all of the cores of the system. And this is pretty time consuming. So actually performing the reconfiguration is very, very fast. So this is less than 2 milliseconds here. But waiting for all of the eBPF programs on all of the cores to check in and say, okay, I'm not tracking anything, that ends up taking quite a bit longer. And this is where you get, and notice this is a log scale. So this is the part that kills you on this workload right here. So essentially, when you wait longer between world stops, the world stop gets a lot more expensive, as implemented here. And then the other interesting thing here is that, yes?
Are you sure, so when you run this multi-threaded, and you get the world stop, you're basically doing a barrier.
Yeah.
Are you sure that, the delay all ascribable to your system? Are you waiting in the barrier for people to complete, or is it like a thread, like the application just happens to have a slow thread, and therefore by definition it takes a long time for that barrier to happen? It's not really a problem in your system.
So this is running, so the system overall pretends as if there's a multi-threaded workload running, even if there isn't.
And it's running kind of in lockstep. You're kind of
Yes.
expecting that every thread, if we do a world stop, every thread should be able to respond.
I'll
Yeah.
rephrase just a little bit here. So
I forget, you do the world stop with the signal version, or?
no, it's the shared memory.
So you're basically every thread needs to hold a shared memory. You know? So you're waiting until they happen to hold.
Yes. And then report back through shared memory that got caught. So that's a slow mechanism. So there's two issues with this. One, it's not an optimized mechanism, and two, it's actually not a necessary mechanism for single-threaded workloads.
Sure.
Which is what we're evaluating here. Asterisk future work. We'll talk about it in a minute. So another important note here is the overhead of, so when we're in this world stop, the underlying application is not continuing, it is not stopped. We're stopping the sampling, which is, there's two parallel tracks going. There's a kernel level sampling that's happening and the user level application. So all this is we're waiting to hear from the eBPF program that we've turned off sampling, because if we continue to sample while we're mixing around the counters, we're not going to be able to ascribe those intermediate samples to a particular
So
event.
you're waiting on world stop with BPF
Exactly.
threads in the kernel, basically.
Yes.
Okay.
And yes.
Does that mean that those orange bars are effectively downtime when you just don't have any coverage?
Precisely. And we'll get to that in a second. So the neat thing though is, because of our simulation mechanism, although this is a problem if you wanted to actually use Saccade to do profiling, we can still use Saccade to explore the space of estimators and schedulers despite this performance problem. So we'll start by looking at the column filter configurations. And Nikos, your intuition that there's a problem here turns out to be exactly correct. Notice that this is a log scale, again, going to 10 to the 9th. So
What are the axes?
so on the bot, so this is two different, we are only looking at the two schedulers that actually get used in real life, round robin and rate of change, across our workloads. And then, so the blue dot is an EMA, just basic smoothing. Vertical is the median normalized root mean squared error. So if you take that ground truth sweep trace that I had at the beginning, imagine you got two of those. You take the mean squared error across the rows, you normalize those values to the average value of the counter, and then you take the median column-wise. That's where you get this number. And there's a question about how do you characterize what a good result is. And any one number you pick is going to hide a lot of complexity. This seemed like a good strategy to get an overall sense of how the schedule is performing. But let's go back to this. So we've got this line here is a ballpark of like what is actually usable. From a profiling perspective, our square here, the green square, is a naive configuration of the column filter. So we don't do any off-diagonal process noise seeding. All we do is we set a sensitivity in a sort of a sensible middle ground and let it do its thing, let it figure out the correlation by itself. And that seems to do pretty well. And it does, in fact, beat EMA on one of the workloads, and it's very close on this other. The analytical column filter configuration, which is the triangle, what we do is on those common filter training workloads we saw before in the methodology slide, we compute the Pearson correlation of the counters across entire corpus of trace data, and then you use those to seed the process noise with off-diagonal values, and hoping to encode the correlation between the counters in real life, and so that when the noise gets added, it gets added in the right spot, and when you make an observation somewhere, then the noise gets, or the uncertainty gets reduced in multiple places. Turns out that that performs astonishingly poorly. So the intuition here is that, and then expert is we take that and then we also throw in a few more correlations that we know about from knowing things about the AMD Zen 4 architecture. So things like, there are many counters that are just aliases for each other, so we can say those are likely going to be exactly the same. And it's in the noise, really. Still a pretty catastrophic performance. Although I will say a little better, but I cannot make a quantitative statement about that. They're still terrible. The intuition that modeling this as a linear system of Gaussians is a bad way to model this is exactly correct, because counter noise is, depending on where you're at, if it's very low latency, it ends up being more of a Poisson distribution, and then at a phase change, it ends up being pretty fat-tailed. So modeling it as a Gaussian is not necessarily the most accurate way to do it, and of course the linearity assumption comes back to bite us too. So if we zoom in though a little bit on the configuration that actually works reasonably well, we see we do get a pretty significant improvement on this deep string workload, and that is the highest noise workload. It's sort of baseline noise in the system, the hardest to learn about. And we'll see that the EMA does perform quite well in that particular, the Kalman filter performs very well in that particular workload. Everything else is very steady state stable. This one has a lot of changes and stuff. So let's move on to the accuracy profiling. And so this is, the big slide. Don't freak out about all the numbers. I'll walk you through it in a second. This is all of the different configurations that we have. Yes?
Remind me, what's your ground truth again?
So the ground truth is collected using that sweep mechanism. So it's an imperfect measurement of the real application, but it is representative of what an application looks like, and we can compare to it. Because we're not running the application, collecting ground truth, and then running the application again and collecting our results. We're replaying that quote-unquote ground truth through our scheduler. So even if our ground truth isn't perfect, we're still using it as the basis for our
It's basically everything comes with the same exact assumptions of what has happened.
Yeah.
Thank you.
So, yeah, we'll take a look here on the right first. So each row is a different configuration. So we've got round robin, random, max uncertainty, all the way down to our very fancy reasoning dynamic LLM scheduler. Each column is a workload in the same order we've seen them so far, and we've got the three different estimator configurations in each group. And so, what are the top value here? There's no chance of reading it. Don't worry. The top number here is the normalized root mean squared error on that workload, and then we've got the standard deviation. The colors are where this is really important, because we're trying to see, can we beat consistently random? That's all we're trying to do, beat random.
So, just a dumb question. So they are all scheduled. So if I look at a particular row here, dynamic LLM.
Yeah.
So it's a combination of the
Scheduler,
and
estimator.
the estimator, and the ordering from top to bottom is not significant.
Not significant, it's just consistent.
Okay. Sorry.
I would say broadly,
The columns are the benchmarks.
yes.
Gotcha.
So what we're looking for here is
Yes.
any configuration that can consistently beat random. And so our colors here, if it's more amber, it loses to random. We're normalizing against this random EMA error. If it's the amber color, it's losing to random. If it's a blue color, it's winning against random. And it's a log scale. So this dark blue here is about you know, half of what we see up there, and then, you know, this guy is you get the idea here. The important thing to note is that while random EMA is never the best, we cannot find a scheduler that can consistently beat it across workloads.
What's special about the spec 5.3 workload?
This guy?
Yeah.
It's much noisier.
What's the name? I cannot read from here.
Deeps Jang. It's the
Oh, okay,
chess
yeah,
engine.
yeah.
It's much noisier.
It's a hash table.
It's much, so it's a hash table. And, well, I mean, presumably it's a min-max tree.
It's a hash table. I looked at that, it's all hash table.
Oh, yeah, look at the board state.
It's all looking at the board state of the hash table. That's 90%.
So the order of the benchmarks from the two charts is the same, right?
Yes.
I can read the line.
Yeah.
So
So,
good.
so I'm gonna go through a little bit of it here. So, just to take a few, this is sort of it's actually like a 3D thing that we're trying to make 2D, and so it's hard to read. So what we'll do is we'll take a section of it. This figure here represents just these 3 rows. So this is all of our round robin ones. Oh, and also one thing I'll add. Every LLM configuration got 5 runs. Every analytical configuration got 10 runs. And so that's where we get these standard deviations. And also one more note is that these schedules themselves, what we do to make the schedule non-deterministic, because if you run the schedule around robin on the same workload, you're going to get the same results if you start at the same place. So what I do is you take your world of all of your events, and before you start, you just shuffle it around. So you get your starting configurations a little different every time. So instead of, what we're trying to do is we're trying to avoid saying, oh, it just got lucky that one time and picked, like this scheduler happened to line up with things nicely. We want to get a broader sense of it. And you'll notice that the standard deviation on the chess engine here is higher than, on average, than the others. So under round robin or EMA, the simple estimator performs pretty well. And then this is common with that naive configuration. So we're giving it a fair chance. Interestingly, if we go over to the max uncertainty estimator, now this is the max uncertainty scheduler. Now this is not as good of a scheduler as round robin, you know that, but it is a scheduler that is very close. So what we're doing is we're looking at our estimation of the state and we're picking events with the highest uncertainty. So having a good estimate of the uncertainty is going to help our schedule. And we find that Kalman does give us, even with all its caveats, it does give us the best estimate of the true uncertainty of our estimations. And it does beat EMA with the exception of integer sort and that guy whose name escapes me right now. Cool. And then if we go down to something a little more exotic like our dynamic LLM, even though it does have a feedback loop where you're feeding your estimates back into the schedule generation routine, it's not at a high enough frequency to make much of a difference, and the EMA's better smoothing wins out. I'm going to move on. If anyone, okay. I'm going to move on. There we go. So now we're going to try to compare our simulation runs to the real hardware. So we've done all this work to find our best configurations. Why not, actually use those configurations to try to learn something about an application? So we're going to pick just our 2 bigger ones here. And we're also going to compare it to using perf, because that's there. It should be pretty good. Perf has some advantages, because the overhead of perf switching counter configurations is much lower than Saccade, because it has full-blown kernel support for it. And so we actually get some interesting results here. So this is the coverage. So this is how many, if we take that trace that we saw at the beginning and we divide it up into a 2-dimensional grid, and we say, what percentage of those grids actually, those cells actually have an observation? How good's our coverage? We see that in Magic La La Land, where we're not modeling the cost of changing, reconfiguring counters, we get very, very good coverage, which is what we'd expect. We're simulating it. But in the real world, we're with the simplest, the baseline schedule, which is a round robin and propagate, which is very similar to what Perf did in 2010-ish. We actually get competitive coverage to Perf. Not quite as good, again, because we have to pay overhead, but we do get competitive coverage. The question is, does that result in a better output? And the answer is not really. For deep string, running Perf on real hardware beats even our simulations. But on the image magic workload, we find that our simulations actually do beat Perf. So if we can get the overhead of reconfiguring the counters down, there's no reason to believe we couldn't get this level of performance on the real hardware. Now we're going to look a little bit at the LLM guidance. So all of the LLM schedulers take an optional guidance parameter, which is where you say to the scheduler, I am interested in the memory hierarchy, or I think that in natural language you say, I think that these kinds of information are going to be the most useful for my analysis. And for this example, we just said, I'm interested in the memory hierarchy, focus on that. And I, as the performance engineer, I know that those tend to be more interesting counters regardless, so maybe we'll give it a little bit of help here. And we find that it definitely can dramatically improve performance. So on image magic, it got the reasoning static LLM from outlier bad performance, bang in line with the rest of them, outside of the margin of error on these runs. And then we got pretty compelling performance on deep string with both the dynamic LLM and the reasoning static LLM, but it degraded the performance of the weighted round robin LLM scheduler. This is just a brief survey of it. This is not an in-depth analysis of why this happened. This is more of an observation of the dynamics of this system.
Is this the simulation?
Yes, these are in simulation.
So what exactly constitutes headroom here?
So the headroom here is we're saying there is room to improve this. The noise floor of this workload tends to be around here. So an otherwise poorly performing scheduler can be brought in line with the rest of them, is what I'm getting at here.
Well, this is a simulation, so you know what that ground is.
Yeah.
So you know what the noise is.
Exactly. And so, based off of all this, I promised you that I would give you a configuration recommendation. Am I really going to recommend that you use a random scheduler? No, I'm not. Round robin is just about as good. It's not much better, but it's a little better on most of the workloads. So I'm going to recommend that to you, round robin with EMA. You can sample as frequently as you want with this mechanism. So if you want to sample every microsecond, go for it. Keep the scheduling quantum, at least with the current implementation of counter swaps, at or below 100 milliseconds. And if you have a specific region of interest that you really want to learn about, the reasoning static LLM scheduler can get you better performance. The dynamic LLM scheduler does not appear to have significantly better performance than the static one. And so limitations, we've talked about a few of these already. The key one is the hardware. So if we could convince AMD or Intel to give us a chip with 30 performance counters, that would be fantastic. They probably want to use that for their X3D cache stuff, right? Giving up that much space is just not acceptable to them, especially for something that's going to be used so rarely. The majority of time in Saccade is spent adjusting the counter configurations when at runtime. That's a tremendous opportunity for optimization. The linear Gaussian assumption of the Kalman filter does come back to bite us. And for short workloads, the dynamic LLM schedulers make no sense because we would have to wait longer than the workload to get a new schedule back. All of the usual LLM reproducibility issues apply here. I did my best to mitigate them. I've not gone into depth here on how. And a couple other, the headline quality metric is imperfect because we're comparing two, very large matrices to each other essentially. And how can you attempt to quantitatively understand the quality of that, of the difference between those two things in a single number? So it's an imperfect metric. I think it is still useful for the things we've been talking about. And also the analytical scheduler implementations are reasonably naive. So there is a project called Tintin that I read about where they have a very cool scheduler. They completely replace much of the perf kernel infrastructure and use a very, very cool scheduler. They have the custom accelerators who run their own ML model. There's very cool options here. We kept it simple for this. And future work. So big one I've already talked about, reducing the tax on swapping. Better state estimation, an extended common filter or unscented common filter would perform much better here, I think. And then a particle filter doesn't even make the Gaussian, or makes even fewer assumptions than the others, and that could perform exceptionally well. Advanced analytical schedulers I've already mentioned. There's no reason you couldn't do a learned scheduler here through this interface, using your reinforcement learning techniques that you all know about. Now, most of the infrastructure is there for multi-threaded workloads and system-wide monitoring, but that was not included as a part of this analysis. And so where do we land? Performance counters are scarce, but the events worth observing are not. This is the core problem we're trying to solve. Saccade is not just a profiler, it's a framework for evaluating profiler configurations. I presented a family of estimators, analytical schedulers, and LLM-driven schedulers, and evaluated them, finding there's no straightforward winner. And the space is worth exploring. There is room to improve here, but now we can with these tools. And so, to put a button on this, this is why I think you should give me a degree. I built 2 servers for FPGA development. That was a ton of fun. Amazing experience. I got to do some really cool research, 4-ish papers worth of research. I'm really proud of it. I got pretty good grades. And I ran a gajillion interviews for CS13, and I learned a ton. And so, from the very bottom of my heart, this is the last time I get to talk to all of you like this. Thank you. I'm so happy I was here for the last 2 years. I learned from each and every one of you, except for the folks who I don't really know yet, but it's good to meet you. This has been an amazing experience, and I'm really happy to have done it, so thank you. And I will happily answer any of your questions to the best of my ability.
Could you go back to the first RMSE lots? So
These guys?
Yeah. So like any of these. So these are the error relative to the ground truth for across all of the 222 metrics that you've been measuring, and the ground truth is you've taken a trace of every single of all of them, and then you're comparing that to a single run.
A single run over that ground truth. So our collection of quote-unquote ground truth may be imperfect, but instead of running an actual application underneath the scheduler, we're going to feed that ground truth through the scheduler. So it's a virtual counter source. Is that what you're getting at?
So just to be clear, you run it, you have the application, you pick counters 0 through 3,
Yep.
you run it. You pick counters 4 through 7, you run it.
Mm-hmm.
You're assuming it's a deterministic application.
Yeah, and these workloads are
Yeah, and they are. And you join these
phase
together,
ones.
and now you have like counters 0 to 255, whatever.
with normalization.
Yeah, normalization. And that's basically the trace that you are trying to recall it ground truth.
Trying to reconstruct it.
So where I'm going with this is there some way you can did you look at like determining some minimal set of counters that are like the most critical ones that everything else is correlated with, and like those are the ones that you like schedule the most heavily, or yeah, that's
So not in a, I did not look at that in an explicit way. The hope, so the idea behind this configuration right here, max uncertainty column, is kind of the, I think I'm gonna push back a little bit on the framing, because if you have a counter that's highly correlated with a lot of other things, you actually want to schedule that less often, because you're going to be hitting all of the things that it's correlated with.
yeah. So I'm saying
Right.
Yeah, so I'm saying if those are all correlated, then you should pick one of those and never sample the others.
That's the idea behind this, because if you observe one of those things in that cluster, it will decrease the uncertainty for all of the things in that cluster. Is the theory behind that.
Okay.
And we find that maybe this is just a poor implementation of that idea. The hope is that even with the this one, the hope was that the analytical and the expert configurations would encode a lot of those correlations. But for whatever reason, I would claim the Kalman filter not really being an accurate model of the system, the underlying system. Introducing those causes it to blow up. And it causes it to blow up with like, these are not like the Kalman filter is giving bad predictions. These are the Kalman filter is breaking and the math is breaking down. It is that bad when you do that. Because the assumptions underneath the Kalman filter are a linear Gaussian system. And if your system does not match those prerequisites, then it starts to break down. So if you did like a histogram filter would probably perform pretty well here, or a particle filter, because those make fewer assumptions. Although, that being said, tackling the challenge you mentioned explicitly, and instead of using something that tries to identify those, you know, online, doing something where you load up, perhaps you have something a little bit more exotic. I'm not sure what that would look like. You could do like an imputing model or something would probably be a sensible architecture for that. Lots of space to explore. Yes.
Quick follow-up to that. Do you actually see that the error is uniform across the events that you're measuring? Or is it that in some of these, like if I say over here at the top, your best K performing events in terms of estimation, and minimizing error there, which one of these performs the best? Because like here was saying, I don't need to get all these events.
Yep.
I need a couple of them. And if, essentially what I'm saying is that by doing the median and normalizing all these between each other, you're essentially
Losing a lot of granularity.
yeah, you're losing a lot of that granularity, and essentially for all of these ones that are trying to do a smarter scheduling,
Yeah.
they're going to be ignoring some of the other counters. So they'll be inherently making those errors worse. Unless your estimator is very good at identifying across
Yes.
which I think we've seen your estimator's not good at estimating across.
This one is certainly.
Yeah. So none of these are really good at measuring error across these events.
Mhm.
So you're being punished for focusing on one event.
Yes.
More so than any one of these schedulers you can say is really bad or not doing well, I think. It's because
Perhaps.
there's too many independent variables. So.
I agree. I think though, I don't know if you're being punished for because you'd expect with like a propagation filter or a propagation estimation, if you have a lot of counters that are very low variance and you're not sampling those very often, the propagate filter is going to continue to perform fairly well. And that's what we see.
But I have a lot of events like memory events where
Yeah.
I with the last level cache miss. If I only measure last level cache misses and I don't measure L2 cache miss and I don't measure L1 cache miss,
Sure.
then I'm missing on two counters, but I hit on the counter that matters the most.
Absolutely.
You'll get punished if your estimator doesn't understand that a last level cache miss implies an L2 and an L1.
Sure. There's a gray area though, where there are a great number of these counters that are either aliased to other, or there are a great number of events that are either aliased to other events or very, very rarely even trigger. So the hope is maybe your more advanced schedulers will look at those less often, the stuff that's either aliased or boring, largely, and focus on the interesting things. That is the hope, and why I think, even though this is, I fully admit this is an imperfect evaluation metric, I think it's still useful. And I think looking at like the 90th percentile, you know, taking the top 10% like you suggested, totally give you a very different result. Although I don't think that would invalidate these results.
No, I'm not. These results are valid. I'm not saying they're invalid. Overall, you're not good at estimating all of the events with these fancier schedulers
Yep.
and all these estimators. I'm saying that you're hiding the fact that with your system you can get really good at focusing on certain events. Because of the way that you're measuring your system,
Sure.
you're cheapening your own. You're making your own system look bad, basically.
I think so.
You're making the fancy stuff look bad. Because the way that you're measuring this doesn't actually help fancy things.
Sure.
Fundamentally,
In the
try-
absence of a better
if
estimate.
you're trying to optimize for minimizing error across the board. To minimize error across the board, I want to have random selection. I want to randomly probe all my signals. So,
Although, I don't think that's
It
true.
depends on the nature of the signal, right?
If
there's-
it's noise,
if
sure.
there's 222 of them, and really only 10 of them are moving in interesting ways.
Then why? Here's the question: then why aren't we able to narrow it down? Why aren't we able to narrow in on the 10 that are moving in interesting ways?
Because your estimator is doing a bad job of saying that all the things that aren't changing aren't
Well,
changing.
you're trying to optimize for something different what Tommy's talking about, right? I mean, so
Sure.
your goal is to reconstruct the entire state of the system,
That's the goal.
right? That's the measurable. And I think your goal, Tommy, is more like, tell me what the interesting fact.
Yeah, I thought this was something for like, I'm a performance engineer and I only want to do one run of my
Yeah.
system, but I want to get all the events out of it, but I only want to focus on the events that actually matter.
I mean, that's a fair, I mean, definitely that would be a tool that would be very useful, but I think your goal was how do you construct the entire state of the system?
That's the broad.
Okay, if that's the goal, then yeah, you need all the events.
Because that way, you're not, I mean, I think originally when we were talking about this, the idea was something like, we reconstruct the entire state of the system, run something like this all the time, and then see if the state of the system changes in interesting ways, the whole system changes in interesting ways, is indicative of something that maybe a path or something like that. And then it stayed at this, when we reconstruct the entire state. Because another kind of question here is you have this 255 element vector, whatever it is, that's evolving across time. How much actual information is in there? The fact that you have a lot of these correlations, really suggests
There are strong correlations.
there are, for sure. But the thing is, the more correlation you have, the less information. you
Exactly.
have.
Yeah. And so the idea then would be, okay, the hope with this filter here, and then the dynamic ones is you would narrow in on a set of representative counters for each cluster, and you would be able to get, you would waste less time observing things that you already know stuff about. That's the theory behind it. I think that if I had had more time, I would have loved to dig into the behavior.
Just to be clear about that, so the focus here, right, focusing on the counters that you can actually measure. The goal of that focus is to be able to reconstruct them all.
Yeah.
As opposed to finding the
Pick
ones that are most interesting.
the best ones.
Yeah. So, can you imagine changing the system so it would try to find the best ones?
Absolutely. What you would end up looking, first of all, you get a better filter and you pick the ones with the highest variance. That would be the naive way to do it.
What if you wanted to find the ones that are changing? Suppose you took like the derivative of
Sure.
the boundary, and then you
That's-
What would that be?
That is very similar to what the rate of change does. And so that picks the things that have the highest first reviews, essentially. Short, recent history first review.
So it picks the ones that are highest rate of change, but what if your idea is like, I wanna focus on the counters dynamically, and you wanna focus on the counters where I see the highest rate of change, so I'm basically try to kind of find change.
Yeah.
Or kind of change.
Yeah, that would be pretty straightforward to attach on this. You could even, if we go all the way back to our architecture here, we could.
Liam, I hear you have an entire system built and a bunch of trace data built.
I sure did.
Others might be able to.
I just put 400 gigabytes in one tank.
Yes.
So
So there's lots of great ideas.
there are a lot of great ideas
that
here,
you can leverage, Liam.
and I'm on Slack. But if you wanted to do trace detection, you could plug that in here as a sink. That wouldn't be too terrible. Or sorry, change point detection. You could plug that in as a sink. That wouldn't be too terrible. Any other questions? Yes.
Follow-up question on zoning LLM, specifically dynamic LLM. What's the latency of your LLM that you're running here?
Great question. Let's kick over just so you have something to look at.
You can just give me a ballpark and say it's on the order of minutes.
So it's not on the order of minutes. It's not like that. So here's what I did. I ran this local. I ran I did a run to characterize the latency when I use a local GPU developer. That gives you a ballpark. I had a freaking figure for this, but it didn't make it into the presentation. It's in the paper. You end up with it being ballpark 30 to 60 seconds with a long tail.
Okay.
A long, narrow tail. So occasionally you get something that's like 100. A couple times you get a 200 second. But so how this actually ran in real life, because I did not want to wait around for Dubliner's present but limited GPU to run these things, is I simulated the latency and used cloud resources to run to run the models. And so the grand total, this is 170 million tokens were spent on this, ballpark across 8,000 queries, 9,000 queries, $20. I have the model details in here too. It's the Gemma 4 26 billion model. The largest one we could fit in.
Is 30 to 60 seconds, is it operating with stale data at that point or no? Is it making decisions on stale data?
It's making decisions on stale data, but if I go back here to the very beginning, like what stale means depends on where
I'm
you
asking
are,
if
right?
is it stale?
Yes, obviously,
In
but
practice, is it stale or not at 30 to 60 seconds for what you're looking for?
well, in practice, what it means is this is not useful for the NAS workloads because those are too short.
Yeah, but
Um,
it's done by then.
It's done. The workload is done by then.
Would it matter if the workload didn't have multiple phases?
Absolutely. I mean, if it was a single phase workload, it would be trivial. But if you
Yeah, it's not stale, but it is stale.
if you lose, if you miss it's not going to be that bad for that long, I guess. I mean, it's lagging, but if you miss a phase transition, you'll pick it up in the next one. So, not surprised.
Just a comment here. I understand your ground truth, but when you try to apply some of these things in actual performance, hardware performance counters coming from an actual system, the different events come with different accuracy measure.
Yes.
There are some counters that are notoriously bad. Like, I don't remember the exact one, but there was one back, like a few years back when I was looking at TLB misses. That was up to 50% off. I mean, that's like a random number generator at this point.
Yeah.
So, having knowledge of the inherent uncertainty of the counter as it comes from the system is something that could help you tune your system, because this is not variability that you see because of whatever your design
Yeah.
is variability coming from the counter. Even if you have the identical same sequence of events, your counter is in la la la.
And that would be the measurement here in the filters. That itself has, you can encode a noise on that.
Right.
It's the obvious place to insert that, and then that gets baked in this whole update loop. Yeah, that would be a very, very helpful extension with a better filter.
And every system is different. I mean,
Yeah.
one version of a processor to another, it's like, drastically things. They fix X, they break Y. And has never been fully fixed.
One of the things I looked at was also the counter skid.
What counter what?
Counter skid, like where if you attribute a TLD-ness to an instruction,
Yeah.
it might have happened a dozen instructions ago, and you're only finding out about it now because the counters are not precise in the architectural context.
Yeah.
Anything else?
Yeah, it's not, so another kind of interesting thing is, so so Intel will actually use models for, I don't want to say about performance, but for the power and energy counters. They actually explicitly tell you that you're not actually getting a measurement of power and energy. You're getting an output of our model that's estimating power and energy based on whatnot. So it's not inconceivable to believe that you could actually produce better than their ground numbers by reinterpreting their output of the model. But in any event, there's no question. I do have a question though. So one thing that these performance counters can do, right, is that they can fire an interrupt.
Yes.
So is there a way, have you thought about like how you can take advantage of that as opposed to thinking about this in a periodic way? Because you can't think about this periodic across time, but you could do like periodic across
Event driven. So I think a way that would make sense to handle that is you characterize, you bin all of your counters into event driven or time sampling. So there's a big set of counters which you will see one event per 10 seconds, something like that. What you can do is you can say, I don't even care about sampling those things. I'm just going to configure the overflow interrupts to fire and say overflow at 1. And we'll get an interrupt on all those things. And that can get handled separately. You could even, because this is eBPF driven, you could do a custom handler in the eBPF, and it would never even get into the kernel in its own sense. It would just land in your user space program through shared memory. It would be.
You could conceivably like try to predict the rate at which the particular event happens, and then use that to set the interrupt, set the overall interrupt rate from performance events to be
Yes.
fixed, or something like that. Anyway,
The challenge, though, actually,
nothing for you to do there. Just
all the challenge is I don't know this, but I don't think you can set. I may be wrong with this. I don't know if you can set an interrupt on something you're not counting. Because
No,
if
you can't. You're right.
Yeah.
You're right. You can't. That, okay. Yeah. Okay. So it's not gonna. I mean, that makes sense.
although I suppose there's not.
You can't because if they really don't count something.
That's the challenge. I mean, one of the original ideas here is I was going to ask Carl to whip up a version of Boom with 250 performance counters on it to get the ground truth, but this was a little easier.
Small matter of program. It's a nice big for them, I swear. You just gotta go find
Chisel's
them
great.
first.
Chisel's great.
You
Trust
just
me.
gotta find them all first.
Trust me, bro. Any other questions? All right. Thank you all very much.